Just follow it through.
PC to. So. MAR. So you put it on. You put it on the B bus. You don't need the LU. So
you work backwards pretty much.
I mean,
That's
sort
what
of.
Jacob said.
Yeah. I don't really know which way is technically forward. So.
He's alive.
Yeah, so I can go over some problems.
That would be greatly appreciated.
Anyone's in particular?
Just trying to do 1A real quick.
And I should, in theory, be recording this, so.
So, are you gonna do what you did yesterday, where you like just teach us basically what the lecture was, or no?
I mean, I have no clue what was covered in the lecture. And if the lecture was basically just this sheet that got sent in the...
No, it was not the sheet. It was like this sheet, but more complicated.
It was breaking down each of the equations step by step.
That's the same thing that I talked about the last time. It's just, getting practice with it. So, this is for all horizontal stuff, the question 1?
Does not specify.
It must be.
Yeah.
If it's asking,
for
the
the table.
Okay, so I'm gonna go through all of them, but any particular question from those that from like A through G that you'd want me to cover?
I think you could do B.
Sure.
Thanks.
And wait. So what I was talking about with going backwards, the idea here is that you want to start from where you want to put something and go back to what you want to put into it. So here we want MAR equals PC. So start MAR here. Well, if I go this way, I'm obviously not going to get to the PC register, which is up here. So I've got to go the other direction. I'll use red for this. So in order to get to the MAR, got to come back up here, all the way to PC. That has to go through the B bus. There's no way to go through the A bus to do that. Then you've got the MBR equals AC. So, well, the only way to write to the MBR, if you can see it, is this little arrow here pointing into the MBR. So that tells you that that's what the input is. And so we can take that to start going backwards. We can't go up here because this is how we're writing to these, and we don't want to write to one of these registers. We want to read from AC. So we're not going to go up this way. Oh, must be. 1 second. Yeah, whatever. That should be fine. Let me redraw that other line. All right. Yeah, so it can't, it's not going to come up from here. That's just not going to actually do anything. So we have to come all the way back here, through the shifter, through the ALU. Now, again, one thing to keep in mind is that this is also going to be going this way here. So we can't possibly have this B come through this way. That just wouldn't work because there's already something there. So it would have to come from over here. Now for the AMUX, you could come from the MBR, or you could come from the A bus. Obviously can't come from the MBR because we want to put the AC in the MBR. It's going to have to come through AMUX here, and finally just all the way up here onto back to AC. And there's just this write operation. So once you have this picture, you're pretty much done. Just answer all of these questions. AMUX, where's it coming from? A latch or MBR? Well, clearly A latch. So we can look at the instruction key up here and see that it has to be a 0. Condition. Well, condition, there's no conditions in this operation here. If you look at like question F, that has that if n go to 0, that's when the condition is going to come into play, or D, where it says go to 25. So condition here is just going to be 0. ALU, well, here we have these two inputs coming in, and we only want this blue line here to pass through. And so that's going to be the A operation of the ALU, just the pass through, which is operation number 2. Shift, we want the data just to go straight through the shifter without anything happening, so we want to do no shift. Now for MBR, we're writing something to the MBR, so MBR is going to be 1. MAR, we're writing something to the MAR, so it's going to be 1. Read is not in this instruction, so it's 0. Write, it's right here, so 1. For enable C, we want to look here and we want to see if we're assigning any of these registers here. And we're not doing like PC equals something or A equals something. It's only MAR and MBR. So this enable C is going to be 0 because we're not writing back to a register. Then C here would be the address of the register we're writing to, but we're not writing to a register. So it doesn't matter what we put here because regardless, the enable C is 0. So it's not going to write anything. For the B bus, well, clearly we can see that we need PC to be read on the B bus. So that means B is going to be 0. Then AC needs to be read onto the A bus. So A is going to be 1 because AC is the 1 register. And then address here, our condition is 0. So the address is ignored anyways because we're not doing any sort of branching. And so you should get this as your answer. Any questions on that?
Why was B0?
Because on the B bus here, which register do we want to put onto the B bus?
PC.
PC? What register number is PC?
Oh, okay.
Yeah, so for right here, you put the register number that you want. Keep in mind, this A, B, and C have absolutely nothing to do with these. They're completely and entirely different. These are just some general purpose registers called A, B, and C. These right here refer to what you're reading onto the A, B, and C bus. So this isn't asking what's the value of the A, B, or C register. It's asking which register do you want to read out onto the A and B bus or write to from the C bus.
I'm sorry, what'd you say address was don't care?
The condition here, so the address is going to be used if we do something like if n go to 65, right? This right here is the address. So we don't have anything like that in this instruction. So the address is don't care because condition here we're going to set to no jump.
Okay, thank you so much.
Yeah. And the main reason for that is that your instructions are going to be laid out in your memory essentially sequentially. So you'll have one instruction, then the next one, and the next one, then the next one. And by default, when a CPU is executing, it just keeps running down this line of instructions. It just keeps going. But it can see an instruction and say, okay, well, if a certain condition is true, then actually just go back up to this instruction or some other instruction. And then it'll just keep moving along. Once you get to actually dealing with VML, you'll see that this is how it works. It just kind of goes down the line of each of the instructions, and then at some point it might say, okay, well actually I'm going to jump back up to here. So the default here is no condition, and no condition means just go to the next one. Or no jump, sorry. Any other questions on this one? All right. Does anyone want me to do another one from question 1 or go to question 2?
Can we do F?
Yeah. So the B and it's just
That's
and.
cheating.
It's just I don't know why syntax wise we use B and for that, but it's just the and operation on the
He
CPU.
said
Are you doing
F.
F?
Yeah.
SG.
Oh, sorry, F. Yeah. Okay, yeah. Let me see here. What layer is this on? Okay, so we've got a whole bunch of stuff going on here. TIR equals. I'll just do ls for this, for left shift. Save some space. And then if n go to 0. So first of all, can anybody tell me, can anybody describe what this operation is doing? It's doing IR plus IR, and then it's doing a left shift, which will result in what? So IR plus IR will double IR, right? And what does left shifting a number do?
Moves the bits by 1.
Which has an effect of doing what?
It can make the number negative.
Multiply it.
It multiplies it by 2, right?
Oh,
So like, you know, if this is the number 5, right, which it is, if you shift it to the left, it becomes 10,
I didn't know that.
and then 20, and so on, right? Because 5 is 2 to the power of 2 plus 2 to the power of 0, right? 1, 0, 1. And then if you shift it, then you're basically changing this 2 to the power of 0 to 2 to the power of 1, this 2 to the power of 2 to 2 to the power of 3, which is just the same thing as multiplying everything by 2. So when you left shift, it multiplies by 2. And so doing this operation here, TIR equals left shift IR plus IR, it's basically doing TIR equals 4 times IR. So just something useful to note is that left shifting is used for multiplication, or can be used for multiplication. And you will learn more about that in one of the future labs. So yeah, we can just start looking at how everything needs to be processed. So the TIR register is right here. We'll start just backtracking. So, yeah, oh, I think I'm on the wrong. Oh, never mind. That's just adding more stuff. Okay. So we're trying to put something into TIR. So we'll start from the input of the TIR, work backwards, got to go down all the way over here to here. Now there's no reason to go to the left here because that's an input into the MBR, so we're not going to be able to read anything. So that means it has to come from over here, has to come through the shifter. And here the shifter, we want to do a left shift, and the shifter is the only thing that can actually do the left shift. So we know that this right here is going to be doing a left shift. Then we're also doing an addition. The only thing that can do addition is the ALU, so the ALU has to be set to addition. And then sort of we need both of these on the side, both of the inputs to the ALU here to be IR, because we're trying to do IR plus IR. So this is going to have to go to IR, and the other one's going to have to go to IR. And that's pretty much it for the data flow. So you can go ahead and start actually running out the different aspects. So first one, AMUX. Clearly data is coming from the A latch, so that means AMUX has to be 0. Condition, well, we have a jump if n equals 1, right? We're doing if n, that means we're going to do the jump if n is 1. So that means the condition is going to be a 1. Then we have the ALU operation. Already figured out over here that we have to make it do addition. Addition is operation 0. The shift, we want it to do a left shift. So shift left 1 bit, that's operation 2 for the shifter. MBR, well, we're not writing anything to the MBR. We're not writing anything to the MAR. We're not doing a read. We're not doing a write. However, we are writing to a register, right? taking something up this C bus and into the TIR. So that means this enable C is going to have to be 1. So then C, well, what register are we writing to? We're writing to the TIR register. That's register number 4. So C is 4. B, for the B bus, we'll look on the B bus here. We can see that we're reading IR, which is register 3. So B is going to be 3. On the A bus, we're trying to read from IR, which is register 3. So A is also 3. And then the address here, we're doing go to 0. So the address is 0. Any questions?
Is this basically what all these kind of questions are going to be like?
Yep. For the horizontal, at least.
Did he cover anything farther than that for this previous lecture?
I mean, in the last lecture, he also covered the vertical microarchitecture. I don't know what he covered today.
I'm pretty sure this was pretty much as far as he went today.
Yeah, so he was probably just going back over and looking at questions. So let me see here. So within this class, it's less important to be able to go from one of these operations to actually filling out this table here. In reality, filling out this table is ultimately what the goal is to be able to do. So given any architecture and how this table works and what the architecture looks like, can you figure out how to do something? So in reality, you shouldn't just look at these examples here and say, okay, well, how can I make them? You should be able to come up with literally any operation or literally anything you might want to do and do the translation. And it should be obvious how the translation needs to happen. There's occasionally situations where you can do multiple there's multiple ways to do it, but typically there's only one way to ever do anything on an architecture, or at least definitely a best way to do it on the architecture. So let's see. I could go over another question from part 1, but they're essentially all the same. It's all just about figuring out how the data needs to move along, and how to actually, and then from there, just knowing how to answer the questions to actually fill out this table. But they're all fairly basic questions.
Is horizontal usually easier than vertical?
No.
It's not.
Horizontal, it actually matters how the architecture is laid out. With vertical, it does not matter at all how the architecture is actually laid out. Because with the vertical, you're given a set of instructions you're basically given how the system functions and how you are supposed to interact with the system, rather than essentially being given all of the controls. It's essentially a step up in abstraction between hardware and full-blown programming. First thing you have is essentially a horizontal architecture where you have a whole bunch of switches everywhere that you have to manually configure to get every instruction for every instruction to get them to all work right. Then you can move up to something a bit more vertical where you have basic operations. Then you can move up to an assembly language like VMAL where it gives you the ability to do labels. So rather than having to say jump to line number 3645, you can say jump to this convenient label I placed here. Then you can, from there, you can maybe program a language like C. C would compile to the assembly language, which would then be translated to the vertical microarchitecture, which internally in the hardware gets translated to the horizontal. So the higher up you are, the more familiar it is to programming. So I would say vertical is probably easier, because it actually doesn't matter how the hardware works. So let's see. Then there's question number 2 is translate the ones above with the vertical. So I'll go ahead and do the 2 that I covered with vertical instead of horizontal. I'll actually swap. so you see this whole opcode thing, opdecode. So that right there is essentially doing the job of computing what this table needs to be, given one of these kind of higher level instructions. So you give it the op, and based off of what the op is, it automatically generates a table like this that you see gets wired absolutely everywhere throughout the core in order to actually perform anything. So the first one I did was the MAR equals PC, MBR equals AC, and so on. Right, so we have MAR equals PC, MBR equals AC, and then right. So let me see here. Let me get a bigger copy of the table here. Can I make that bigger? Oh well, let's just look at the table then. Okay. So for this, first step to do is to translate this instruction, this code here, we can call it, to a set of instructions that the hardware can natively do, and that's all of these instructions here. That's all of the instructions laid out in this table. So you might think when you're starting out with this problem, you say, okay, you have MAR equals PC, so that would be operation 0 here, right? Because you have the MAR equals X, where X is just some register. Then you have MBR equals AC, so you might think, oh, that's operation 4 afterwards. And then you have the right, so that's operation 3. But that would be wrong, because if you look closer, you see there's op 15 here, which does all three of those at the same time. So that's something you need to be careful of, is just whenever you're looking at these operations, make sure you look through the whole table to figure out the best sequence of operations. So we can do this in one instruction. So we can just go ahead and directly start filling out the table. So op, R1, and then R2. So the op here is 15. Right, so MAR equals X. Here we can see that X should be PC. PC is register 0. And we can see here that X goes into R1. So that means R1 is going to be 0. So you're just kind of matching the pattern of the instruction that you're trying to do to the pattern that's specified on the table. So MAR equals X. Here we're doing MAR equals PC. So that means X equals PC. And then PC here we see is register 0. And then X here we see gets assigned to R1. Just all just looking up the table. So that means that R1 is 0. Then we have MBR equals AC. AC, over here we have MBR equals Y. So that means AC is Y. AC is register 1, and Y gets put as R2. So that means there's going to be a 1 there. And there you go. It's the whole thing. That's it. Didn't even look at the architecture. You just look at the table. You do need to know these register numbers, but you can look those up. You'll be given this sheet. So, but yeah, that's pretty much it for the vertical. You just look up the table and fill it out. Any questions on this one? All right, I'll go on to F, which this one does get a bit more difficult because we do have to split it up into multiple instructions. So we have TIR equals left shift IR plus IR, and then if N go to 0. Okay, so clearly we cannot do TIR equals left shift IR plus IR. There is nothing in this instruction set that basically says X colon equals left shift Y plus Y. If there was something in this table that could do that, then we could do the TIR equals all of that in one instruction, but we can't. What we can do, however, is some more basic operations. We can do like X equals X plus Y, or X equals Y, or X equals left shift Y, or something like that. So one thing in general that you want to do when you're working in assembly is you do not want to change the value of any register that holds a value that you're you're using to generate a result. So here, when you're doing IR plus IR, I should not do IR colon equals IR plus IR, because that changes the value of IR. And this instruction potentially, like the programmer might use IR again later on, right? And so you don't want to mess up their register states. But there is one register that you know you can use, and that's TIR, because the programmer is already asking you to change what TIR is, so they obviously don't care what's currently in it. So here, you might start off with something like TIR equals IR plus IR. However, if you pay close attention, there is still nothing in this set of instructions that allows you to do this. The only addition operation is X equals X plus Y. There is no X equals Y plus Y, or something like that. Right? So we cannot do TIR equals IR plus IR in one instruction, let alone all of this stuff. So the first thing that we're going to start off with is just TIR equals IR. Now, TIR holds IR, so now we can do TIR equals TIR plus IR, right? So this first instruction corresponds to op number 11, right? We have X equals Y. Those are two different registers. That's fine. Over here, now we have X equals X plus Y. That's another instruction. So that means that's good. Then we have to do a left shift. So then we could do TIR equals left shift TIR. And although this instruction is listed as X equals left shift Y, X and Y can still be the same thing. So this still fits one of the patterns. It fits the pattern of operation 14, right? Then we have to do the whole if n go to 0, and we do have an operation 7 here that can do that. But with the vertical microarchitecture, it's important to know that the n and z flags don't automatically get set for anything. There is a specific operation, namely operation 5, that does set the n and z flags. And so anytime you want to use n or z, you have to do the ALU equals x nz operation. So the next operation here is going to be ALU equals TIR. And the reason we're using TIR here is because TIR is what we're storing the resulting operation in. And so what this if n means is essentially after this operation is performed, if TIR is negative, then go to 0. So here we're doing ALU equals TIR, and then we're going to set the n and z flags here. And this is just an arbitrary syntax. It doesn't really mean much, but what's essentially happening is just you're basically figuring out whether TIR is negative and 0, and then just setting two like D latches on the actual circuit, like right here, that just store that information. And so we'll do that, and then finally we can do the if n go to 0. So here, that's just a built-in operation. So we can do the if n go to 0, and that is all of the operations. These are all valid operations according to this table, and so that means that we can implement this function in the vertical microarchitecture. And so now you would start with actually doing the conversions. So let's see here. Kind of running out of room. Whatever. I'll just start off and I can scroll down if I need. So we have our op, R1, and R2. So the first operation, that's operation number 11. And then here we have x equals y. So it's x equals y. So that means TIR is x, IR is y. X goes into R1. And then TIR is x. and then 4 is TIR, so that means R1 is 4. And then IR here is Y, which is register number 3, and Y goes to R2, so that means R2 is 3. So we've got this first operation here completed. Then we have the second one here. This is the addition, so that's operation number 9. Again here, X, which is R1, is TIR. R2 here is going to be IR, because we're doing X equals X plus Y. Y corresponds to R2. Y is IR. IR is 3, so R2 is 3. So that's the second operation completed. Then you have the third operation, which is the left shift. We see that's operation number 14. Again, X is the thing on the left, Y is the thing on the right. Here they're both IR, so those are both going to be 4. Then we have this operation 5 here. This ALU equals ALU equals TIR NZ. Something to note here is that it says to put whatever register you want as R2. So make sure you're paying attention to the register assignment and how the table needs to be filled out. So I know TIR is register 4, so I'll put that as R2, and then we don't care what R1 is because it's going to be ignored in the actual running of the operation anyways. So that is both this operation and this operation. And then finally we have the if n go to 0. That's operation number 7. And then here the syntax says R1 comma R2 is X. And what that means, so if you look right here, it's a bit harder to see. So if you follow op, you see that op is 4 bits. R1 is 4 bits and R2 is 4 bits. So all of these are 4 bits. In this case, we're just going to 0, so it would, in theory, be possible to fit that into a 4-bit number. But over here, in the vertical, the address is 8 bits. So that means, ideally, in the vertical, we'd also be able to go to an 8-bit number. And so what this syntax means here is that rather than treating R1 and R2 as 2 separate 4-bit binary numbers, you're just going to treat it as one 8-bit binary number. So this whole number here is going to be 0. And I would just write that in the middle here to specify that they're both, like, in combination, the number 0. Any questions?
Yeah, I have one. This isn't specifically about this question, but you were saying that you didn't want to like change the value of the original like IR earlier. Because I was doing some of the labs, and so like you'd want to keep it like the same number, so you wouldn't want to just mess with it. Okay.
Yes, ideally, you never want to change the values because registers are not variables. And that's something that it's a little bit bizarre when you're first dealing with them. They seem like variables, but the thing is there's a limited amount and there's no dynamic allocation. You just have those 16, at least in this case, you just have these 16 registers. And so if you're using a value, if you know you don't need it anymore, then go ahead. You can just like do whatever you want with it. But in general, let's say you have a large program and I give you only one instruction and I tell you, implement this instruction. Well, you don't know whether in a future instruction, whether that value will be used again. Like when you're doing this implementation here, whatever operations you split it up into, it won't magically create a copy. You're editing the IR register, the only one that exists in the whole computer. All programs use the same IR register, which is why there's main memory, so that you can actually store variables outside of the registers. So in general, it's always best to do this. If for some reason, and it is possible to come up with instructions that can't be done just by using the actual like destination register as a temporary register. So like in most cases, you can basically just look at what's on the left-hand side and just treat that as your temporary register that holds all the intermediary results. It is possible to find instructions where that's not the case. You can use the AC register. The AC register stands for accumulator, and the accumulator is dedicated for accumulating results. it's literally the dedicated temporary register. And this is pretty much a case wherever you see the word accumulator, that's what it means. It's just meant to be a temporary register that just will accumulate a result as you're computing it. Sort of in this case, right? So like we start with IR, and then we add IR, and then we left shift it. So we're sort of accumulating a result here. And the sort of semantic definition of the AC register is that it should be temporary and that you should never put anything valuable in it, because at any point in time, someone might use it to store an intermediary result. So if you absolutely need to, you can use the AC register, but otherwise you should just default to trying to use the register you're writing to as a temporary register.
Okay, cool. Thanks.
Any other questions on the vertical microarchitecture questions?
Yes, on the table where it says read or write and it says not applicable,
Mhm.
do we have to write not applicable, or do we have to put like don't care when we are writing down, on the register one?
It doesn't really matter. As long as you indicate that it doesn't really matter what it is. With the read, if you put a 2 in the op here, right, and the 2 comes into this op decode here, and it goes out into the control lines, all it's going to do is it's going to light up this read line over here, and that's it. It's going to do absolutely nothing else. So it doesn't matter what R1 and R2 are, because nothing's going to happen in the CPU anyways. It's all safe. So they're essentially don't cares. But you, like I've seen, you can just maybe like put a line or something saying, hey, I'm not putting anything there because it doesn't matter, or whatever. But
Okay.
But yeah, in general, it's not that big of a deal. Just don't put a value there.
Okay, thank you.
I was going to ask the last instruction, like if and go to. I see you put a 0 for both like things. Is that because it's going to register 0? Because I say it's like.
So it's going to instruction 0.
Okay.
So here, I can talk a little bit about how everything is laid out. So you've got, typically in a computer, you've got the main memory. And the main memory is not physically, but kind of semantically split up into programs and then data that is used within the programs. And this is known as the von Neumann architecture, where you have both programs and data stored in the same place. So then you'll have this. Then you'll have some sort of bus connecting this to the main CPU. So this right here is a CPU. And inside of it, you have registers. And then like an ALU or something. And a whole bunch of other stuff. But typically what happens is that the program counter is going to say, okay, I'm running the instruction which is stored in the memory at a certain location. So what you'll do, what the CPU will do is it'll fetch that instruction from the main memory. So, that instruction might be right here. It'll take it, bring it over here, put it into the PC register, which might be in the register file, or it might be a more dedicated. So you might have a register somewhere that's just dedicated holding the program counter. It'll say, the program counter tells the address of the memory. So it'll say, okay, I'm running the instruction at location, whatever's in the PC register. That might be 0 or something. And so it'll fetch that instruction and then put it into the IR register, the instruction register. And that'll hold what instruction you're doing. Because remember, all of these instructions are essentially just data that can be interpreted as an instruction. So like this instruction right here, the 7-0, this as a number is 0111 for 7, and then just 8 zeros afterwards. So this binary number, whatever it means if the end flag is 1, go to 0. And so what you can read data as instructions, and you can read instructions as data. That's how some exploits are run. Is this you essentially fill the data with code, and then you jump to the location in that data. So in theory, you could say, okay, give me this, put that in the instruction register, and execute that, even though it's data. And so when you're doing go to 0, all it does really is essentially just going to set the PC register to 0. It's just going to set the PC register to 0, and then eventually it'll go get that instruction, get instruction 0, wherever that is. That would be like at the beginning of the memory, and then execute it. With this architecture, it's a little bit bizarre because there is the PC register here, but at the same time, there's also this MPC register, which I'm not quite sure what it is. We haven't really... This architecture is a little bit bizarre. It's not quite what I'm used to seeing, but it doesn't really matter. All that matters is that this is the sort of general model. You have the program stored in memory. You go get the instruction from the memory. You execute that instruction. And where you get it from memory is based off of the location of what you're currently running. And when you do a go-to operation, you're saying, instead of just going from, okay, I'm executing instruction 13, well, the next instruction I'm going to run is 14, then 15, and 16. Instead, when you do a go-to, it just says, okay, well, now instead of executing the next instruction, just execute instruction 0. So go back to the beginning of the program, maybe, or whatever it may be. Any other questions on that? I know I kind of skimmed over the top about how all this stuff is organized, but that's the general idea. This go-to here is just saying go to a different line of code, line 0 of the code. All right.
Thank you.
Let's see. There's translate the following instruction to vertical instructions. That should be relatively easy. So something to note just for future tests, if it just asks you to like implement the function, implement the equation or whatever, then as long as it happens and you essentially don't have any what are known as side effects. So like here, if you would have edited the IR register, that's known as a side effect. So if you're not going to have any side effects and it properly does the instruction, typically it'll be just right, because the goal here is to translate higher level instructions into instructions that can natively be done on the hardware. So yeah, does anyone have any other any questions that they'd like me to answer or problems to go over? All right, well, in that case, I'll probably end the stream and the recording. My office hours are still going to go on until 6:15, so still have like an hour and a half if anyone else has any questions, but I'll just cut this off at that.
Thanks.